the formula for calculating the determinant, if you expand across the first row, is this. The determinant of A is just this. It is the summation from j equals 1 to n. Let me give you the general case where you have it n by n. Okay. Of A1j times C1j. What you're doing, you're holding this I value, which is the row, constant at 1. So that's why it's 1j times C1j. And you multiply first this element 1. That's A11. Let me write this out. In this case, n equals 3. So if I make this substitution, n equals 3, then it would be A11 times C11 plus A12 times C12 plus A13 times C13. Okay. More generally, you would go all the way up to n, but here we only have 3 columns, so we stop at 3. That's it. Now, we've actually done this, haven't we? We have C11, C12, C13. So let's calculate what this determinant is in this case. A11 is what? Anybody? What is little a11? 1. First row, first column, the element is 1. That's this element right here. A11 is 1. What is C11? Well, did I erase that? No, C11 is M11, and M11 was what? Thank you. Okay. So it's 1 times the negative 3. That's C11. Plus A12. A12 is what? 2. Times this cofactor, C12. And C12 is what? It is 6. Plus A13. A13 is what? Anybody? 3. Times C13, and C13 we calculated over there is, so right there, negative 3. So what do we get? Minus 3 plus 12 minus 9 equals 0. Okay, all right. Now, what's nice about this formula, this approach, is actually you can expand across any row you choose. We expanded across the first row. But had we wanted to, we could have expanded across the second row or the third row. Also, we can expand down any column. Now, the only way you have to adjust the formula is this. We assumed we are expanding across the first row. But if we expand across the second row, we would just change the formula as follows. Instead of A1j, it would be A2j. Instead of C1j, it would be C2j. Okay. In other words, we would start with 4, and we would multiply 4 times its cofactor, plus 5 times its cofactor, plus 6 times its cofactor. And the interesting thing is, I'll let you do this, and I'll just assert this. You check it out. If you expand across the second row using this formula, you get the same answer. The same answer for the determinant. You will find it to be 0. No matter which row you choose or which column, if you follow the appropriate formula, you'll get the same answer. Yes? Yes. As we discussed last class, this indicates that the 3 column vectors are linearly dependent.
You only have to do one column to find out, like you have to do all of them.
Right. No. What you would do, Lucy, you have the freedom to choose which row or which column you want to use. Now, in certain cases, it might save you some work if you chose one row as opposed to another row, or if you chose one column as opposed to another column. For example, suppose our matrix was this, Lucy. Suppose I changed this last row to be 0, 0, 1. And if you wanted to find the determinant of this matrix, Lucy, which row would be best to choose? Yeah, the last row, because you got 2 zeros there. So that means when you go across the third row, 0 times anything's going to be 0, plus another 0 here. So all you would have to do to calculate this one is multiply 1 times its cofactor. That's why it's helpful to know these formulas, is because you can pick and choose which row and column. Okay. And in this case, you would want to use this formula. You would expand across the third row. So this would be a 3, and this would be a 3. Okay. And it would be very simple. It would just be 1 times its cofactor. Now, sometimes you might want to go down a column. Now, if you're going down a column, for example, if you are going down the first column, then the formula would be this. Let's say down the first column. Okay. Now you would do the summation. Now you'd be going down the first column. So what would be changing? Not the j value. The j value would be 1 if you're going down the first column. So now it would be the summation from I equals 1 to n of a sub I 1 times c sub I 1. You would be using that formula, where I goes, in this case, from 1 to 3. So you go here to here to here. Okay. And that's if you wanted to go down the first column. If you wanted to go down the second column, all you'd have to do is change this to a second. Change this to a 2, because you're holding j equals 2 constant. And you're going from I equals 1 to 3. That would be going down the second column. Okay. Now, what is interesting, and actually I find this rather beautiful, is if you go through these calculations, Lucy, and you do it for all 3 rows and all 3 columns, you get 0. If you go back to that original matrix. If you go back to the original matrix before I modified it, no matter which row or which column you choose, you'll get the same answer if you don't make a mistake. Okay. All right, so now you have a thorough understanding of how to calculate determinants. And this formula works for even n by n matrices. So that's why I choose this method. It's just one single method will work for any type of matrix. Any type of square matrix. Because determinants, of course, are only defined for square matrices.